talked by Professor Bruno Figueiredo, please.
Thank you. Okay. I don't have a mouse. No, what is going on? Okay. Okay, good. All right. So I'm going to talk about asymmetry learning. A little bit about myself, so you understand. I work on invariances and equivariances and symmetries in deep learning. So what are symmetries? Symmetries, we know geometrically, right, what a symmetry is. A sphere has rotation symmetry, a butterfly has mirror symmetries. But also in nature, symmetries are a fundamental force where in physics, it essentially describes how the world works. And so, for instance, if you do an experiment and the experiment outcome doesn't depend on when you do it and where you do it, you can prove that symmetry implies conservation of energy. And that was proved by Emily Noether in 1918. So there are a lot of interesting symmetries in machine learning, rotation symmetries for images, translation and rotation symmetries for clouds, permutation symmetries in bags or online shopping carts. X is a mapping of the space of X onto itself, which leaves the object the same. Okay, and the definition of the same depends on your application. So a classical definition of symmetries uses group theory, and I'm going to just give you an idea of how we deal with this symmetry. So consider a group G, which is a set together with some operation. And this binary operation is such that closure holds, its associativity holds, and there is an identity element on this operation. So E is the same as A, and EA is the same as A, and then the inverse exists, okay? So that there is always an inverse for every transformation. And that's very important that for groups, the inverse must exist. So here we have what we call the left group actions. So for a group T and a binary operation dot, with identity element E, consider a set X, which is some input, say an image or a graph or a set or a sequence or a point cloud. Okay, so you define the left group action as if you apply the identity transformation on the input, you get the same input, it doesn't change. And then whenever you apply the transformation, you compound two transformations, it's the same as compounding first the group transformations and then applying to the input. For instance, you can rotate this picture at 90 degrees and then rotate again 90 degrees, or you can rotate one time 180. That's what this is saying. Okay. And if you want to learn more about how, for instance, we apply this type of invariances on images, I highly recommend this tutorial we created. A lot of folks email me saying that they finally understand how invariances work in deep learning by reading this tutorial. And recently, someone sent me an email saying that they got a paper accepted at UVips because they read and they understood and they could do something about it. So I recommend this tutorial we created. Group equivariant and invariant functions are as follows. Uses this notion of group transformation. Okay, so let X and Z be two vector spaces, and F be a function that takes X to Z. Think of that as a neural network. It takes the input and gives you an embedding. Okay, so a G equivariant function is a function where if you apply the transformation G on the input, and then you apply F to get Z, it's the same as applying F first, getting the D, the embedding, and then applying the transformation on the embedding. Okay, so it works the same way. I'm going to give you an example of that soon. This is a G equivariant function. A G invariant function is a function where applying the transformation on the input doesn't change the output of F. Okay, so F is invariant. For instance, if you have a point cloud, your neural network should be invariant to translations usually, right? If you translate the point of the point cloud, it's still the same object. If you think about rotations for images, right? If you rotate your image, then you should output the same thing because it has is the same object, not always. Okay, so symmetries. Let me give you an example, a simple example, not in deep learning, of symmetries of a triangle. So the area of a triangle is going to be invariant to translations. So if I translate an object, the area, if I translate the triangle, the area doesn't change, right? It's invariant to translations. While the centroid of the triangle is equivariant to translation. I can compute the centroid first and then translate the centroid, or I can translate the triangle and then compute the centroid. It's the same thing. Okay, does that make sense? So these are invariant and equivariant functions. So symmetries now are everywhere in machine learning. For instance, if any ML method for drug design needs to be translation, rotation, and permutation invariant over the molecules, because the order of the atoms doesn't matter, their location in relative location in space doesn't really matter. It has to work with any such transformations. For instance, an interesting case is the transformer, right? Transformer is actually an equivariant function, except that you put positional encoders on the input, and that's what makes it, allows it to be permutation sensitive. But if you remove the positional encoding, it's a permutation equivariant function. It will encode the words no matter which order, the same encoding, and the encoding follows the word, right? CNN, for instance, is an example of an approximately equivariant function for translation. So if you have an image and you apply a CNN, here's a feature map. If I translate the image, it's like translation of the feature map, okay? So it's approximately equivariant. And actually, that's one of the defining characteristics of a CNN. Let me give you an example here with disentanglement. Disentanglement is an equivariance. So you have this car, which is red, and then you make it blue, okay? This operation here makes it blue. Or you could apply the neural network on the red car and make it blue on the embedding. And if you make it blue here and apply the neural network, you get the same embedding. So some dimensions of the embedding represent blue, and you can just change that. Okay, that's how we can define disentanglement as an equivariance. Okay, so, and the other things that symmetries can improve in distribution generalization. So for instance, for images, right, if rotation doesn't matter in your task, then there are a lot of works creating convolutional neural networks that are invariant to rotation. Or you can also make it equivariant to rotations if you want. So sets, the order of the elements doesn't matter in the sequence. So there are many neural networks that create representations for sets. And point clouds, the same thing, rotations and translations. So any transformation on the Euclidean group, usually, or SO3, will be invariant to that transformation. So just quickly talk a little bit about some of my work. We developed the notion of symmetrization. That's a general method to design universal G-invariant and G-equivariant neural networks. So these are universal approximators. We use it for graphs and sets, but the idea is more general, and there's a lot of activity now on this front. Also, we talk about use group theory to uncover the theoretical relationship between matrix factorization and graph neural networks. So there is a theoretical relationship between the two, and we know exactly how they work together now. And that is also very exciting because a lot of folks are using this now to create new methods for link prediction and also to improve the existing graph neural networks. And also we do auto-distribution robustness in graphs, relationship between causality and auto-distribution robustness in graph tasks. I'm not going to talk about any of this, but just saying that we use a lot of symmetries to deal with a lot of interesting fundamental problems in deep learning. So today's presentation will be about mostly these two papers where we relate auto-distribution robustness to symmetries and what we call asymmetry learning. So the question is deep learning robust to new deployment environments, right? So let's say Tesla Vision is mostly trained in California, and California is a rich state, so they buy this very expensive root signs that are very nice. And then if you buy data, right, for people talking, it's usually like very nice data, right? It's very clean and nice, so you can listen to people, and you can Alexa can translate, right, what they are saying. But if you go to Indiana, Indiana doesn't care about making fancy street sign. So the Route 25 is like this, okay? That's the sign. And if you go drive your Tesla on Route 25, and there is a semi-truck behind you, the car will brake thinking that this is the speed limit. Okay, because you see, it was trained like this, and route numbers, which don't matter for the car, right? Driving like this, but in Indiana, it's like this. So this is auto distribution. And that knowledge saved my life, literally saved my life. Okay, so the other thing, if you're a parent, you know this, that these voice assistants with your kids screaming on the background, they don't work too well. They should work, but they don't. Because this is out of distribution for the type of training data that you have here. So generally, one challenge is auto distribution when the environment that you are testing your neural network is different than what you have trained on. And this is quite common to see. Auto distribution happens when the test is different than training. And this example you may have seen already, right? This is a common distribution example, and a cow on the beach is auto distribution because you can associate cows with green pastures here, and there is no such association, so your vision system may get a bit confused if it is not designed to survive this type of distribution shift. So this is training, this is test, and it becomes auto distribution. Okay, so I think the solution for this is data augmentation, right? Where pre-deployment, you're going to augment your data to look more like the test distribution. So for images, we tend to rotate the images a little bit, right? So that we can see that the neural network sees rotated images, because convolutional neural networks are not invariant to rotation or equivalent to rotation. But you have to be careful to avoid rotating too much, right? Because for some reason that I don't understand, 6 and 9s are symmetric to rotation, which is bizarre. Here is an example for Tesla. They are dealing with auto distribution. So if there is an accident and you're running on the road and there's a Tesla behind you, you are safe, because they simulate people running on the highway, and therefore their car won't run over you because they have data augmented this condition. Without this, it would go through. Okay, so data augmentation is a way to solve this problem, right? But one thing about data augmentation that it tends to be harder than people think. So here's an example of an auto distribution case of a Tesla self-driving itself through an airplane. And you think, well, who would put as a data augmentation an airplane on the road, right? Well, it happened. You see? So the other thing is that another interesting example is human-driven data augmentation. You ask people to do the augmentation. NLP is a very interesting topic, right? Which is called counterfactual augmented data. Use humans to generate new text reviews with different cases. So that you are more robust out of distribution because humans have created the test data almost. The thing is that unfortunately, this approach is not out of distribution robust. And we can actually prove that a context guessing machine, humans, we always, if you read a text, you guess what the context is, right, to change it, are probably not guaranteed to create data that can train an out of distribution robust classifier. So that's harder than what we initially thought. Now, so the one thing that I've been thinking about is how can we change the way we do deep learning to achieve out of distribution robustness? Do we need to rethink it? So let me show some existing work on out of distribution tasks and spurious associations, where the training distribution is like this, right? We have cows on pastures and camels on sand, and then the neural network may learn a shortcut, say, for instance, focus a bit on the background to produce the label of the animal. And then, of course, then a cow on the beach would be out of distribution for this task. This is a very simple case, and I know that you can engineer a way almost out of this problem, but just to illustrate, it's a deeper problem than what I'm showing here. So why would this be the case? Because the neural network learns spurious associations or shortcuts between the input and the label, right? So here is where our work will start. Inputs, the one thing that is happening right now in terms of dealing with out of distribution robustness is this notion that you can decompose the input into spurious and non-spurious, right? So we have, for instance, so the idea is that if you can separate the spurious part from the true, right? Say the causal part of the label. So Wang and Jordan have this paper where they separate the inputs, and Veitch and al. Also have this paper with the same idea that you can kind of separate the spurious input part of the input to the non-spurious part of the input. Okay. The one thing is that this type of approach doesn't fit all scenarios. It fits few scenarios, but not all of them. Because in some scenarios, the input cannot be decomposed. Let me show you an example. Very simple. If I rotate the dog, all the pixels have changed. There is nothing here. Maybe the center pixel is preserved, but the rest all have changed, right? So there is no notion that you can separate the spurious part from the non-spurious part, right? And there are a lot of transformations like this that affect all the input or most of the input, and then you cannot separate. Okay, so we need some procedure, right? If you're really serious about out of distribution robustness, we need a procedure that's not just separating spurious on the input from non-spurious. We need something different. We also need a general definition of symmetry in machine learning. Okay, and I'm going to explain why. So the existing works talk about symmetries through transformation groups. It's widely used, a lot of work, a lot of activity, and I'm part of the group that is working on this type of neural network. Transformation groups accept the transformation with certain properties, and most importantly, requires all transformation to be variable. And that is the problem. So for instance, if you're doing rotations, you're going to do rotations of 90 degrees because those are invertible rotations for images, right? With these properties make the math easier, but groups are not general enough for many tasks. For instance, in some cases, there are definition of symmetry where the transformation will not be invertible. Okay, you don't have invertible transformation, so then you cannot use groups. So for instance, if you rotate an image by only 30 degrees, you're cropping something. And once you crop, you can't go back, right? Changing the background, for instance, is also non-invertible, right? What was the original background of this image? You don't know. It could have been anything, right? So there are a lot of interesting cases where the transformation is not invertible, so you cannot use groups. So we need a notion of general symmetries, okay, that don't go beyond transformation groups. And so what we do then is to define these general symmetries. Actually, recently, there has been used a category theory to define equivalence relations, or use equivalence relations to define symmetries, more exact using groupoids. And the idea is just, instead of defining the transformation, you just define equivalence relation. So you say this is equivalent to this. And then there are transformations that make this equivalence hold. So like group-based definitions, our transformations need not to be invertible. We're just defining them as equivalence classes. So for instance, for a physics problem, here are two motion of a pendulum, and we are saying that that all the curves that have the same energy, total energy, are the same, are equivalent, which means that phase shifts don't matter. Okay, so it's fine. So while defining equivalency relations, we need to assume only these properties, which are easy which are easy to verify and happens in almost all the applications that we need to deal with. Okay, so our results use equivalence relations rather than transformation groups, and this is very important to be able to generalize to more problems. So here is the interesting part. Once you redefine symmetries this way, let me show you a symmetry that is quite interesting. Supervised classification. We are trying to learn a symmetry. What's the goal? You have a function, say a neural network, that is trying to predict a label y, right? It's taking some input x and with some parameters, some neural weights, and produces y. Let's think for now hard labels, but the theory deals with soft labels also, and also regression. But let's think about hard labels, right? You're trying to decide if this is a cow or a dog or a camel, okay? Then all these inputs that produce the same output will be called symmetric because they are in the same equivalence class. So what you're trying to learn is this symmetric function, the function that outputs the same thing for all the elements of the input that are in the same class, right? And that's a symmetry defined through equivalence relations. And we are trying to learn this from training data. So we are our function is trying to learn a symmetry from training data. So let's see. So what you can say is that supervised classification learning then is the same as learning symmetries from data. That's the problem, okay? If you define symmetries using category theory. Then the classification objective is like this. I give you this image, I give you this image, and they need to be in the same equivalence class. They need to have the same output. So you're trying to find neural weights, they'll be invariant, right? Get the same output to everybody in the equivalence class. That's what we are trying to learn from data. So the auto distribution generalization, then you could say, oh, that's fantastic, because then I'm also trying to learn a symmetry, right? I'm trying to say that all these cows in the grass and in the sand, they're all cows, right? I want to learn the symmetry, which is fantastic. So we can just use the approach that we have used so far, right? Learning symmetries from data. But here's the problem. Is that true? Like, is auto distribution robustness or classification just learning symmetries from data? So what's the problem here is that we don't have the test distribution data. We don't have their cows on the sand, in the sand. So we can't learn this symmetry from the data. It's not in the data, right? So we need to think of a different way to learn the symmetry. But how? How do humans solve this problem, this auto distribution problem? We can easily do this task, right? Let's agree, it's easy for us. How can we do this? So I started thinking that was during COVID when everybody was having deep spots, right? So I started thinking about this problem. And at the same time, I was teaching my son to read, which was also very hard. So So I realized something when I was teaching to him, that he had some very interesting symmetry that he had in his mind. And then I learned that all children like that. And I learned more, much more than that. So here is my son. I told you that he was going to show up in the picture. So, and then what's the difference between the guy on the left with the orange shirt and the guy on the naked guy on the right in black? Okay. I'll be honest with you, some days I don't really know if they are different. They seem to behave very similarly, but what's the fundamental difference in the way that they learn? Okay, do we know? So here is learns this thing, and that was fascinating to me. So young children must be taught asymmetry, while other primates, just like neural networks, they assume input-output relations are asymmetric. So let me explain this. You see this? If you learn B, D, P, and Q are different, right? They are different. If you give a CNN, it will not get them confused. But for him, I have to explain that these are different things, because in his mind, they're all the same. He can't see the difference. Okay, he has to be taught. And this is actually came from the school. All kids are like this. So I dug up, and actually this is one of the defining characteristics of human intelligence. Okay, that unlike apes and all other animals, we assume symmetries. We always assume everything is symmetric until we are shown a case that shows asymmetric. Okay, so if you give training data, E implies D, okay, and D implies Z, both of them learn this relationship, ED, GZ, both of them. But only this guy will assume that D also implies E. Okay, and Z implies D, and moreover, there is a transitive relation that Z implies E. This is a defining characteristic of human intelligence. And this is no, I'm not citing some work that nobody knows. This work has 2,000 citations, 2,500 citations. It's one of the most important works in development psychology. Okay, it's one thing that we know for sure. This guy can learn language, right? But doesn't assume symmetry. That we know for sure. Okay, so knowing this, right? We understand that human level intelligence requires asymmetries to be taught explicitly. Okay, my son was not learning symmetries. He was learning asymmetries. So yes.
So
yes.
So seeing that this kind of asymmetry is not really natural, right? So that means that probably we can try to design a kind of better ways, right?
Oh no, yeah, no, yeah. I mean, after I started really thinking about this, it's insane, right? Why did we design this thing? We designed it. We designed this, right? We did it to ourselves. It makes no sense. Knowing that we assume symmetries. This makes no sense.
Just one like a kid kind of suffer.
Yeah, no, I have actually during dinner we can talk. I have a theory about this. Okay, but actually it's more general than this. It's not I'm giving you a visual example. Oh yeah, oh sorry, I'm looking there. But actually, this is for any stimuli, anything, any relationship, which is very interesting for causality, because for any relationship, this is true. And this has been verified over and over again with many different scenarios. It's not only visual, but it's for everything we learn about the world.
Yeah,
Yes. Yeah.
Humans just think that if he happens, also he happens.
Yeah. So if given a stimulus E, then if you do D, you get a reward. A young child will immediately assume that given the stimulus D, if you do E, you get the same reward.
But also in real life, it doesn't always hold.
It doesn't always hold, yes.
Maybe that is not good for kids to learn asymmetries.
Right, exactly. So if that doesn't hold, you have to be taught explicitly, given data, that this doesn't hold. And then they learn that. So that's how they learn.
So they wouldn't decide this. So maybe also teaching kids that 6 and 9, even though the asymmetries in a sense, they're different meanings. Translating for the divider of UCD doesn't mean he also can.
No, so that is an interesting point, is that being taught one asymmetry, it doesn't change your prior. It's just a prior that we have. It doesn't change the prior. For another different situation, we'll still apply the symmetry. So for instance, when I taught him 6 and 9s are different, that didn't translate into knowing that P and G are different. Like he didn't, I had to teach that specifically also. Yeah, because it's different, yeah. So they apply kind of a context sensitive asymmetry. Yeah, yeah. But apes don't need that. Apes don't need that. They immediately assume that B, G, P, and Q are all different. No, but they can learn language, right? So they learn. This is an experiment with lots of different. Okay, so asymmetry learning changes. So what I want to do with this, right? That is to change the paradigm of learning from learning symmetries, as we saw, to learning asymmetries, rather. And here is where causality enters the picture. So I have all these transformations here that they change X, okay? And my prior is that none of these transformations change Y. So Y is invariant to all transformations. I'm assuming it's symmetric to all these transformations. So now we are ready to talk about auto distribution tasks, right? As a structural causal discovery. We are trying to discover what are the right relationships between the transformation, which transformations affect Y, which don't. Okay, so robustness to auto distribution tasks without examples of the task distribution, right? You don't see the task, examples from the task, requires a causal model. So you need to know what is changing between training and test. The causal model must state symmetries relating training to tasks that can be relevant to label Y. That's one of the things that we show. So let me talk about auto distribution robustness. I'll give an example here of a rod. Here is the training data. We are just trying to predict if this rod is upright or flat in this image. Okay, and then the causal diagram is like this. Rotations of the rod, of course, change the label, and the X and the Y are related somehow, right? There is some association between them. But horizontal translations do not change Y, okay? Only rotations. So horizontal translation is spurious. So let's look at our.
In the previous slide, what do you mean by the dashed line? So you already have a dependence between the previous. Yeah.
Oh, sorry.
So you already have a dependence. Yeah, right. Yeah.
Yeah. So the X doesn't have an arrow to. It's not causal to Y. There is just a confounder here. We're going to see a confounder here that gives Y and X.
In this example, what would be the confounder?
I'm going to show this case. Okay, so let's try to use a neural network to predict the orientation of the rod in this image. So let's first start with this X dagger, which is a hidden untransformed input on some canonical order, for instance, this one. And then what we are going to do is we are going to rotate or translate this X dagger to create X. X is what we see. So The shaded variable is what we see. So, so here we have a 90-degree rotations and horizontal translations to get the x. For instance, if we apply, we have two rotations in this example, 0 degrees, then there is a 0 pixel translation, 90 degrees rotation, and a 5 pixel translation. So this is going to work like this. You do a 0 degree rotation, 0 pixels translation, horizontal translation, and then you get a 90 degree rotation, and then a 5 pixel translation, horizontal translation, okay? And that's what you obtain in the end. Now, the transformations, of course, here affect the entire image, right? That's important. Now, what about y? So y is only defined by what was the original input, the x dagger, and the rotation, okay? That's what affects y. So if you get something like this, it's going to be flat, and label does not depend on horizontal translation. Doesn't matter how the horizontal translation is, the label doesn't matter. Okay, so this is just this example, right? This simple causal DAG here. The DAGs that we are, the more general case for us will be something have many transformations that y depends on, and some set of transformations that are spurious with respect to y, only affect x. Okay? Important that we want to predict label y from the observed input x. I think a lot of folks that when we talk about causality in auto-distribution robustness think, well, what is causal about auto-distribution, right? Because the task itself is association. I'm giving you some input, and you just need to predict the probability of the label. That's it. It's an association. It's not causal. You're not trying to make a do operation here. That's the task. But the causal part is for the following. But learning to be robust to the changes requires distinguishing spurious versus causal transformations. You see, if you don't identify the spurious transformation, you cannot be invariant to them. You see, that I think that's the important thing. Even though the tacit association of the learning is causal, needs to learn to understand the DAG, right? The causal relationships. So we do another thing that's important is we do not know a priori which transformations affect y. So we have to learn, find a way to find them. So the training data we assume is what we call economically sampled. What does that mean? It means that since horizontal translations do not affect y, anybody that will give you data will not give you many different horizontal translations because it doesn't matter. If you look at ImageNet, there are not that many pictures that are upside down, right? Everything is kind of canonically oriented because it doesn't matter. You see? So in training, we will not see all variations of this transformation, okay, of the spurious transformation. And that's the problem that we have. So for instance, our training data, we'll see things like this. All the horizontal translations will be 0. And when we see upright and flat like this, that's our training data, because why would you give it differently since it doesn't matter? Okay, so the test data generated from the same structural causal model, but in the test, we have values of the horizontal transformation that you have not seen in training. So now in real life, your users are going to use your camera upside down. Have you tried in the iPhone, try to unlock your phone upside down? It doesn't work. Oh, it worked. Oh, it's a new iOS. Finally, we fixed it. Oh man, now I don't have an example. You see, I used to give this example in class, and then Android fixed it. And then the Android users would be like, oh, it works. No, professor, it worked. And the iPhone users would be like, wow, yeah, it doesn't work. Now I don't have an example, like they both fixed. But your user use your camera differently, right, than what you imagine, the canonical orientation, and that will be spurious for your task. Okay, so for example, we can give first a horizontal translation of 5 pixels in the first round. And if we do that, if I translate 5 pixels and then rotate, look where the rod is. Very different position than you saw in training. Okay, so traditional data augmentation, the idea is to apply the transformations so that your classifier is invariant to those transformations. That has seen all these examples in the training data. But here's why it doesn't work very well in some cases. All your data is like this, right? Translated, this rod is not up here. It's just going to move around here. You see, just augmenting your data with the transformation you know you need to be invariant to is not enough. So the traditional data augmentation is sufficient to train an auto-distribution robust classifier. And that we are going to see a lot of the approaches that we have been using for data augmentation fail because of this. So here is a function where it works perfectly in training and works perfectly if you translate the training data. So if your data augmented, it works perfectly. It's this function where you see this band here, it counts the pixels on this band. And if there are too many pixels on this band, it says it's flat. If there are few pixels on this band, it says it's upright. This is the function, okay? And this function works perfectly with the data augmentation. It works, it always predicts correctly. Now look at what happens out of distribution. There are no pixels in the band. So it will say it's upright, right? Because that's the rule that works perfectly in training and with your data augmentation. Okay, so we need a counterfactual definition of data augmentation for that. So the counterfactual variables like this, I see this X in training data, and I ask, what would this X look like if I had done the horizontal translation first, before the rotation? And now that what the data looks like is like this. I'm not going to go too much into details, but what you need to do is something called abduction. You need to try to come up with all the possible cases where if you change the horizontal translations, you'll see different ways in which the rod is going to end up, depending on what are the possible transformations that created this image, okay? So for instance, here, we are going to see the rod being up here and the rod just being translated here. So this one now, if you use this data, this is something that you will be able to see in tasks. So this type of counterfactual data augmentation would work. The traditional data augmentation doesn't in this setting. So we need a counterfactual definition for data augmentation. And when I mean counterfactual, I mean the counterfactual in the causal sense, not counterfactual in other sense. There is another sense of counterfactual that's not actually counterfactual in the causal sense. So auto-distribution robustness must be symmetric to all spurious counterfactual inputs, okay? That's the symmetry. So therefore, we need to define robustness as a counterfactually invariant symmetry. Like, that's how we define it. And that's the definition we have, is the notion of counterfactual invariance, that the neural network doesn't care, it gives the same output, even if you were to counterfactually change the data. So it's symmetric to the transformation that you would see in tests, okay? And there is also a definition that Veit gave at the same time, but the thing is that their definition is very restrictive for no reason. Like our definition is more, also talks about the counterfactual case, which I think is a better way. I also, okay, notation-wise, please, if you ever talk about this, please use our notation. This is much easier to understand for people that do causality. What they did is very difficult. We had to read multiple times and wonder what the notation was. Please use our notation. Just as a FYI. So the learning task then becomes a causal structural discovery. We need a classifier that's counterfactually invariant to spurious transformations. That's what we need. That is, find the correct causal graph out of the following. Just an example, okay? Oh, it's here. So we have, so we start with this, that none of the transformations affect Y. And we're trying to find whether this edge, if is this edge that exists, or this edge that exists, or maybe both edges that exist, or none of the edges that exist. We need to know that to be able to invariant those changes, right? That could be spurious. So the classifier should not be invariant to transformation that causally affect Y. And now I'm going to talk about how is that related to my son's thing about learning asymmetries, right? So we are going to define this. And let me just show that, give a bit of an idea of what the type of theorems we have in the paper. So we defined the equivalence relation to be lumpable. We have a definition for lumpability respect to all symmetry transformations. And that means that if there is, the causal DAG has an edge between the transformation I and Y, if essentially the predictor for Y is, if it's invariant to transformation I, then if it doesn't affect, essentially, if being invariant to the transformation doesn't affect the predicted performance, if the relationship is lumpable, then we can find a causal edge. So let me go quickly then over this. There's a notion of lumpable. I'm going to skip over this. It's essentially like a generalization of a billion groups for things that are not invertible. And let me explain this part. So how is that related to, so finding the right structure then is essentially what my son was doing. So we can assign a score to any allowed causal graph, okay? So all these possible graphs of how the transformations change X and Y, we can assign a score. And then we can essentially minimize, try to find think about this. So if I give you this asymmetry data, right? If you were to think that letters are all symmetric with respect to rotations and flips and translations, you would not get this right? You would make mistakes here. Then this data is telling you that your neural network cannot be invariant, symmetric to rotations and flips. That's what it's saying. And you can find that from the data, because if you are invariant, you won't be able to do this task. And then you know that you have to be sensitive to this transformation. But translation is one that you can be invariant, right? It doesn't matter what the letters appear, they're always the same. So that you can be symmetric about. Essentially, that's how this procedure works. And we use a minimum description length to do that. And the search that we do to find the right causal structure is a greedy search, okay? To find a local minimum score, you can try to work towards a global, but in all the applications we used, the local was also the global, so we didn't have to work on that. Okay, so let me, I'm going to skip this. It's essentially, this is a physics problem that we have a symmetry, and then we show that asymmetry learning works. We have in the paper also examples with images. I'm going to skip over this result since we started late, but it just works to imagine that every paper, it works, right? So it works. And we can find the right causal structure. There are some industrial applications for this that we are working on, both asymmetry learning and counterfactual invariance. For instance, we have a robust visual quality control in the factory floor to changes in illumination, and we use asymmetry learning to learn what's the right types of spurious relationships between the images and the defects. We also talk about recommender systems using causality with the same ideas, because link prediction, recommender systems are causal problems, effectively. And graphs have lots of symmetries. And then condition-based engine maintenance, maintaining an engine, looking at vibrations, it has to be counterfactually invariant to changes in the RPM. So if the engine goes faster, the vibration changes, but the condition of the engine has not changed. So this kind of vibration with respect to RPMs is spurious. And also the one interesting one, also counterfactual data augmentation We use, we are working with Amazon specifically because they have Thursday night football and everybody wants to watch football in 4K. Their service cannot handle the load. And people are complaining they don't get their 4K, that they pay their TVs, very expensive TVs to watch on. So we are doing this counterfactual data augmentation so they can test new algorithms without doing A/B tests. You don't want to do A/B testing. Users get very mad when you do A/B testing because it degrades the performance. So we want to be able to answer this as a counterfactual query, like what would have happened if I had changed the algorithm this way and without actually evaluating on users. And with that, I'll say this. Why am I so excited about this? It's because this is an intersection between symmetry, deep learning, and causality. And a question that I have is human level AI, you see, related to this? Like, can we achieve human level AI if we merge causality and symmetries? Because that's what our brain is doing, right? And we know that is one of the principles. Of course, we are very far from this, but if someone from the future came and said, "Hey, we finally got human level AI, and we use symmetries," I would not be surprised, right? Symmetries and causality. I'm like, okay, yeah, I guess that makes sense. If there were other techniques, I would be, wow, really? But this makes sense. And the reason why I think it makes sense is because if you're familiar with physics, for instance, symmetries are deep down in nature. Okay, it's a fundamental principle of the world we live in. And we know that they are fundamental principle of how we distinguish ourselves from other animals. So it's a very interesting topic, right? That in terms of like, we have been working on learning symmetries for a long time in machine learning. What if we started working towards learning asymmetry, the way that our brain works? But of course, any such a task, right? You have to start small. And starting small for me will be out of distribution robustness, a very simple task, well-defined. We propose a concept of counterfactual invariant neural networks via asymmetry transformations. We propose defining symmetries via equivalence relations and category theory, which will be very important to the future. And also learning out of distribution robustness needs a causal structure discovery. You have to know what is spurious. Moreover, we propose asymmetry learning to perform this causal structure discovery for out of distribution robustness by learning the asymmetries. And with that, I'm going to end my talk. Thanks so much for your attention.
So now we have time for any questions? Okay.
Yeah.
So, the subject and the background, right? So I won't say. Like the problem is the same complexity between multiple subjects.
Yeah. So there you have multiple subjects. You have so here's an interesting thing, right? For this case, you have to define what the equivalence means. Like what is the symmetry that you're supposed to be learning?
Between the background or the subject?
Yeah, because if people are considered, some people are considered background, and some people are considered foreground. You need to define what is the symmetry that you're trying to accomplish. See, your neural network is not even a person, right? You have to tell the person like what is that you're trying to do. There are a lot of groups in Vision that I know of that have been very interested in asymmetry learning. The challenge is right now, how do we define the equivalences and how we build neural networks that are invariant to those equivalences. But I think it's a very interesting topic to explore. So you have to define an invariance to the background people, and then you do asymmetry learning.
Questions?
Yes.
I wonder, as you mentioned that you assume that the data set is economically something.
Economic example, yeah.
Is it a necessary condition for your model to train to?
No, no, it's not necessary, but it's important to be economically sampled because so economically sampled means explains why the learning symmetries from data fails, because you don't have all the transformations in the data to learn the symmetry in the data. It's not there. So you have to assume all symmetries and then learn what is the asymmetries that you need for your data. And then in test, you'll be robust to those changes.
Have you ever considered like we can in turn kind of utilize this to because if we can observe some transformations appear in the data set, for example, the rotation 90 degrees in there, and then we know that it might be a causal transformation.
Right. That, but then it doesn't seem to affect y, right? Then you are like, okay, it doesn't affect y, and it doesn't matter. You know that it doesn't matter, and now you can learn the symmetry from the data because you see all the rotation, and none of them matter. You see it for y. But if you never see a rotation, then how do you know? You see, a neural network would not know. Like an ape, it assumes that they're different, right? When you rotate, things are different and gives a different output. So you have to have a kind of a prior that all symmetries are relevant, unless you see an example. So if your data have the rotation, it doesn't change y, you see the symmetry learning will be fine. I'm like, okay, doesn't matter, right? My prior seems to be correct. Yeah.
So maybe I can ask some questions.
Yes.
So cool. First of all, usually causality that what if I just do the invariant instead of causality? I will not say it's a causal model, right? I just have a mathematical model.
Yeah.
But I have some invariance. You know, causal model is a higher at another level. It's different from say invariant representation.
Yeah.
So what if I avoid using causality?
I see.
I say some relations or some dependent relations are just invariant.
Right. So you're saying is causality really necessary for this
Exactly.
problem, right?
Yeah.
Like,
and maybe here, if you show the diagrams.
it's getting there. Okay.
Yeah.
Yes. So the thing is that if you see, I don't see the effect of any of this on the data. Like, well, I don't see the effect of this on the data. Okay, yeah. The translation. I don't see it.
Yeah, condition. I just conditional independence. I just define, say, why something that is a conditionally, say, independent from the translate.
Right. Yeah, but the thing is that if you define a conditional independence, it might not work as well, because the problem is that if this is not lumpable, it means that a translation, you need to be a little bit invariant to rotations in order to be invariant to translation. So if translation rotations don't have this property because they are lumpable, but in some transformations, one affects the other. So to be invariant to this, you need to be a little invariant to the one that matters.
It doesn't matter, right? You can just introduce some kind of dependence from say rotation to y.
Yeah, but you
model. So in other words, right? When we use causality, essentially you want to see the effects on the intervention. And
right.
Here,
yes.
Everything that as you just mentioned, right? Everything is observational. I just want to make.
Yeah, exactly. The task is just association, right? Yes, that's the task. The problem with not knowing what are the arrows here is that you see you are seeing some transformations, yes. Not all. Yes. So your data, the conditional, you don't have information about how the distribution will change in test because you only see the associations in training.
Exactly.
So how do you know how it changes in test? The only way to know how to change in test would be if you know how the mechanism works. You see?
Yeah. The problem is when you say it's mechanism, you have to make stronger assumptions.
Yes.
Yes. Yeah. So essentially, say, oh, But now, actually, to the problem of, say, out of distribution generalization may not really require the description of the mechanism.
But for you to know, that's a very good discussion. I love it. Okay, so for you to know that your method is invariant to the changes that will happen,
Yeah.
you essentially need to know where is the counterfactual invariance part.
Yeah.
You need to know that is invariant to the counterfactual data.
When you hit the counterfactual, right, you already assume that I have a causal model.
Right, yeah, because otherwise, how would you know how it changes? You see, you don't know how the test changes. So how can you be invariant to that thing that you have no idea? You have to use something higher than the associations. You see?
Exactly. So it's an invariance.
Right.
But I mean, invariance is a kind of higher level because invariance essentially is it's at a higher level than dependence. Because invariance is about how relation will change, right?
Right.
But causality is another level up.
Yes.
Right. It's yeah, that's cool actually.
No, we can. I think that's a very interesting discussion. I don't love that.
Another thing, as you just mentioned. So, in some cases, a certain operation doesn't matter. But in some cases, if you talk about the letters, right?
Yeah.
In some operations, say rotation or flipping, right?
Right.
Matter.
Yes.
So in that case, we think kind of the operation U, some kind of U and X orthogonal or X invariant part would be dependent. The content would depend on what kind of operation you can apply.
Yes.
Yeah, so you may have
So
U and X.
one of the things we prove, for instance, that counterfactual invariance is stronger than invariance. Being invariant to do out of distribution.
Yeah.
Robustness.
Yeah,
They need to be invariant to counterfactual changes.
Yeah, but I mean here maybe you have to introduce a link between X orthogonal
Oh, so this one?
and U, because you can see what operation you can apply would be dependent on the underlying things you are talking about.
Yeah.
So
Okay.
they are also dependent, right?
But they could, yeah, this, you mean, this two could be
It
dependent.
could be dependent.
Yeah,
on
yeah, yeah.
That part on X part, X orthogonal, the one. You
Oh, this one.
Yes.
Yeah.
Right. So what?
Oh, they could be dependent. Yeah. We assume that right now that they are not.
I see. Okay.
But you are right that maybe they could be dependent, and then it's a whole mess.
Yeah, actually, yeah, in your example, indeed, they are dependent because when you talk about the letters, you have to care about the self-flipping. But when you talk about say object recognition, like if you try to recognize whether it's dog, you don't care about this kind of.
No, yeah, the letters in this case, like the letter starts, say every letter starts with a B.
Yeah.
And then you rotate and you flip to make it a Q or a B, a D. You see, like you can make other letters, and then the Y will depend on those operations.
Yeah, exactly.
Yeah.
Okay. So on the technical side, the one last thing, you use the MDL to find the link.
Yeah.
In this case, everything is how do you optimize MDL? I'm just very curious.
Oh yeah. I can talk to you offline. Yeah, we have an interesting way to define the notion of how many bits you need to encode this causal model.
Yeah, that's kind of clearly non-trivial, right?
Yeah.
Cool. So wonderful. Now, is there any question online? No. Okay. Wonderful. We have lots of minutes. Do you have any questions?
Yes.
Maybe I just follow a little bit about the discussion. I'm wondering how do you define the different transformations under different scenarios, like for digits or for different complex animals you need to recognize the type.
Yeah, I think the difficult part right now is that the symmetry prior, right? It's conditioned on you knowing what the transformations are. So you cannot learn right now. We don't know how to learn this transformation. It's not clear to us how it is because it's not in the data. If it's not in the data, how are you supposed to learn? So you have to define it. It has to come as a prior. But it's interesting evolution somehow learned, right? So there is possibly a way of learning something. But at the same time, if you are able to learn everything, then you see causality would be able to solve, essentially you would be able to solve a different distribution, knowing nothing about it, knowing no mechanism, and that's not possible. So there is something that you must bring to the table, like going to an upper level, causal level. You have to learn, you have to know something, but I think there's a lot we can also learn.
Okay, wonderful. So we are running out of time. Let's thank our speaker Bruno again. Thank you very much.